So, welcome back to the next session on Introductory Material Science and Engineering course. It's titled Cornerstone Ideas in Material Science and Engineering, as all of you know. So, the program today would be a recapitulation and goal posting of some of the things we have done as far as pedagogy and andragogy is concerned, and also a little bit of the recap as far as content is concerned. The other things that I'm planning to do today include something called knowledge maps, mind maps, concept maps, and scaffolding. We have already introduced you to the idea of scaffolding in the context of an active cooperative learning environment. Over and above this, we will be having some discussions on properties, and especially in the context of properties, I'll give you an example of how something called Bloom's taxonomy can be used to get students to think in a very creative manner. Okay. So it turns out that it's at the highest level in the knowledge pyramid, and very often teachers think that they have to walk students in a very linear manner through the knowledge pyramid, but that's not really the case, and I'll give you an example of that in this course itself. So that's by and large the program for this session. So a quick recap as far as pedagogy is concerned. So we looked at some key words when it comes to education research, namely pedagogy, andragogy, and pedagogy. So I will not repeat it. It is available in the screen. And we have also spoken about teaching learning environment. This is an example of a relatively reasonable ACL enabled environment or ACL enabling environment, because of the fact that in this you will find that students are sitting together, they can face one another, they can discuss with one another, and so on. So we also told you about the Malaviya Hall in electrical engineering and how the setting there is helpful in facilitating discussions among students and so on. So we discussed what active cooperative learning is, and increasingly, as I told you, there is evidence that learning is not about sitting and listening in a passive manner, but it is about doing, and there is a very strong correlation between performance as far as students are concerned, demonstrated through activities in the class, and learning outcomes. And learning outcome, by the way, is a key word, and we will come to that in just a while. So we also discussed something called guided reading writing, very important for those of us who would like to give instructional materials to students. You have seen Think, Pair, Share as part of these sessions, wherein I have asked students to talk to one another, come up with solutions to problems that have been posed here, and so on. Participatory learning, this is in fact ACL or active cooperative learning is an example of participatory learning, and in fact participatory learning happens throughout our life. We learn constantly from one another and so on. Scaffolding, I had introduced you to the idea of scaffolding, and also to a very important idea, that is of minute paper. So scaffolding is the mechanisms that you have in place, the framework that you have in place to facilitate the learner, and you have seen that over the last few sessions I have asked questions at various levels to help the students think, introspect, absorb, assimilate concepts that we are discussing in the class. Minute paper is a very short activity using which you can get feedback from the student or get a sense of the difficulties they might be facing and so on. I've also discussed the idea of teacher as a facilitator as opposed to instructor, a sage on a stage. And here is where we stopped last time, zone of proximal development. So this is really the distance between unaided learner and a learner who can find aid. So for example, if a student left to herself or himself can study, and we are very sure that they will be able to learn something, but in a facilitated manner they would be able to do a little bit more deep learning over the same time span. And so the gap between the two is actually our business. The idea of zone of proximal development is that it is the gap that exists between an aided learner and an unaided learner. And of course, the greater the aid, better the aid, more scientific the aid, the higher will be the learning outcome. So today I will introduce you to the idea of learning outcomes. This is the formal definition that I have written out. So the formal definition is learning outcomes, also called learning objectives in scientific literature, in education research literature, stand for key lessons that the learners will be able to demonstrate. So this is the key. They should be able to demonstrate that they have learned. Okay, and for that you will have to pose questions accordingly. So this is an important activity of the teacher, of the facilitator. So learning outcomes or objectives are key lessons that the learners will be able to demonstrate in a reliable manner. Alright, that means you need to have a certain set of yardsticks that are well defined and so on. The instructor could use the learning outcomes to organize lesson plans using the following key questions. So these are the questions I ask myself when I write out learning outcomes for my students. So for example, what do I want my students to demonstrate? So what do I want them to do, to show to me, alright? And how is it that I can facilitate them by suitable reading materials or discussions or questions and interactions and so on. And how would I test this learning that has occurred in my student? Okay. So how would my student reliably demonstrate the learning they have had? Okay. So typically, learning outcomes should have an action verb because the student has to do. There is a performance involved. There should be a subject connect. So, and I'll give you an example of that. And you should also set the expectation from the student, the level of achievement you anticipate along with the yardsticks that you will use to evaluate the student. This gives the students clarity regarding what is expected of them, and that is really the power of learning outcomes, and that is precisely why it should be used as a pedagogical tool in our classroom settings. Okay? For example, you can set out a learning objective for a certain lesson. The student should be able to calculate XYZ given parameters ABC and should be able to assess the suitability of the material for XABC application. So if you set out a learning objective like this, it is very clear to the student what they are expected, and that enables very systematic education. So before I go forward, I'll give an example of learning outcome in this particular course. Okay, so I will set it out for you right now. Alright, so the learning objective of the next exercise I am going to tell students here to do, and I'll of course give them a recap so that they are comfortable. So the learning objective of the next exercise as far as students are concerned is to see parallel between various thermodynamic phenomena. That means they should be able to use something like, let us say, the second law of thermodynamics. In two independent contexts, and as a consequence appreciate the idea that system is a very generic universal idea. Okay, closed system is a generic universal idea. Isothermal systems are a generic universal idea. So this is an exercise precisely meant to encourage students to think along those lines. Okay, so this is the problem, and before we go to the problem, I'll just give a recap to the students as far as some of the discussions we have had here is concerned. Okay, so in the last few classes we looked at various materials properties. Okay, and for those of you who do not recall, don't worry, or have not heard this before, please do not worry. I just gave a bunch of keywords associated with properties associated with materials, and I got students to think about them. For example, let me go back. So for the benefit of students here who might have missed the earlier sessions, I started out by giving the definition of material science, and I told about the scope of material science and the methods of material science and engineering. We spoke about the materials tetrahedron, alright, and we used the materials tetrahedron to develop project plans. I asked you to use the materials tetrahedron as a template to come up with some project ideas. So this is an example of creative thinking, right? Because typically when you are going through a textbook, you learn it in a very linear manner, but you don't have to. You can actually learn in a rather creative manner. You could ask a question at a higher level and facilitate learning, perhaps even in an accelerated manner. Okay? So this, as a consequence, was an interesting exercise in my opinion. So we classified engineering materials into a wide range of categories, for example, metals, ceramics, polymers, glasses, and so on and so on. We looked at data and tables for physico-chemical properties associated with a wide range of engineering materials. And here in the class, we also tried to see reason for stress-strain curves. We drew stress-strain curves. We tried to analyze stress-strain curves and so on. And I asked question, what must be happening? what must be happening? Can you think about ways in which you could explain these trends? Okay, and that was meant to be an exercise in deductive thinking, in deductive reasoning, and analyzing what is happening, and so on and so on. So subsequent to that, we did discuss properties, particularly mechanical properties. So we looked at the following parameters. Over and above that, we looked at electrical properties, thermal properties, and magnetic properties. So these are the properties that we discussed in the class, as far as I remember. Yes, and I gave you a wide range of data to sort of wrestle with, okay? And I also asked you to come up with your own explanation for thermal expansion coefficient. Why should thermal expansion happen? Okay, and you came up with an explanation for that. We looked at some elementary phase diagrams and asked some interesting questions about that. And here is where we stopped last, which was electrical properties. We defined resistivity, electrical susceptibility, and so on. Okay, and we looked at some of this, these tables. Now let us go down further. And we also looked at eddy currents. You independently came up with some applications for eddy currents. You independently came up with this. So here is a question, and this is a slightly involved question, but I would encourage you to not give up easily. Okay, so I'm going to tell you some facts, and you are going to write down those facts. Okay, and I'm going to give you a question which you can use those facts to solve. All right, when you solve it, you would independently come up with a mechanism for doing refrigeration in this room. Something that is very different from air conditioning. Okay, a new idea altogether. And it's an idea that has been around for long enough, but you will see the parallel as a consequence of these facts and what follows from there on. Okay, so the first fact I want to discuss is the fact that most of the refrigeration systems around, they are based on. That's right. So they are all heat engines in one form or the other. They have some refrigerant that is undergoing thermal cycling. There's no question about it, right? So there is vapor phase, there is compression, there is expansion, and corresponding to that, there is energy transfer. Okay, so you can expect you have a refrigerant, a fluid that is used, and so on. Now you have studied fluids in the past. Okay, you have studied fluids, you have studied about gases and liquids in the past, and so on and so on. Now I am going to make an important statement here, which might help you think about an entirely new way of refrigeration. A magnetic system, okay, is made up of tiny magnets. Think of them as being made up of tiny magnets. Now these tiny magnets are like gas molecules. So the important statement that I am making here is that you have a magnet. The magnet is essentially magnet because of the fact that it's made up of a large number of tiny magnets. If all the tiny magnets are oriented in one direction, you have a large magnet. Okay, if they're all misaligned with respect to one another, it's just like a gas. It's perfectly disordered. It is a high entropy system. Okay, now drawing this analogy between magnetic moments. So these are called magnetic moments. Okay, the tiny magnets that exist in materials and the gases, gas molecules in a container. So here you have magnets, they can be all misaligned. So that is like a gas molecule that is going back and forth, bouncing around, having tremendous entropy because the volume is large. Okay, and here if I order these magnets, it is like having a gaseous system with much lower entropy. It is like having a gaseous system that is confined in a much smaller volume. So do you see the analogy between the two? Now, drawing on this analogy, and you are welcome to use your devices, you are welcome to open up your devices, come up with a mechanism by which I will use magnet for refrigeration and not gases. Do you understand the question? So this is a creativity level question. Okay, so you have studied magnets somewhere, you have studied entropy somewhere, and you have studied gases somewhere in your high school. Now I want us to actually learn by developing an analogy. Okay, so do you understand this question? So the facts are the following. Magnets in a solid are like gas molecules in a container. Gas molecules that are highly confined are like magnets that are ordered. Just two facts. Now you can look at refrigeration cycles, and then you draw the refrigeration cycle, and in parallel think about how you can build a magnetic refrigerator or a magnetic AC? You understand the question? You understand the question? Okay. So you are welcome to open your devices and read about refrigeration cycles, look at the refrigeration cycle, and now draw a parallel for a magnetic refrigerator. You understand the question? You understand? So this is a creativity level question. This for the instructors there is at a very high level in what is called as the Bloom's taxonomy, which I know many universities in the country follow. So let me show this Bloom's taxonomy for the benefit of the instructors who are viewing this. So you can discuss with one another. You can open up and start discussing. You can open up data on your favorite search engine and start collating some notes and discussing with one another. So this is the Bloom's taxonomy for the instructors here. So you will find that this question is at the create level, and very often there is a misconception that students in their first year need not be given questions at creation level. They need to be given information at this level, which is mostly memorizing and understanding and rarely application oriented. But I personally believe, and not just me, many educators believe that it is important to give exposure to students at all levels of thinking, because these are just levels of thinking really. And the way in which we ask questions influence the way in which students will start thinking and applying the concepts that they use, they learn, and so on and so on. So this is my firm belief that it's important to ask questions at various levels, even to the youngest of students that you're dealing with. So have you started getting some information? So why don't you just look for refrigeration cycles? So you can draw a refrigeration cycle. There will be a piston that goes back and forth. And then based on the two statements I made, you can actually come up with an analogy for something that uses a magnet. You understand? You understand? So look at Vapour refrigeration cycles. Yes? So there is, so look at what the refrigeration cycle looks like. So it's a cycle, right? Because there is constant transfer of energy from a hot region, from a cold region to the hot region. So you're making the cold region cold, you're retaining this temperature gradient, and so on and so on. So just take a look at refrigeration cycle. So you can use Google Images if you want, because that might be easier for you. So you can just use Google Images and look at refrigeration cycles. So that is the full mechanism. So just look at the cycle. Step 1, is it isothermal or adiabatic? Step 2, is it isothermal or adiabatic? Step 3, is it isothermal or adiabatic? And accordingly think about what the magnetic analog will be. Yeah, that is correct. Vapor compression cycles. So take a look at what vapor compression cycle flowchart looks like.
Vapor compression cycles.
Yeah. You can go to images.google.
Yes, sir. Type
Images.google, and then just type vapor compression cycles. And why don't you discuss with one another? Because some of you must have already started thinking about ways in which you could use this. So is step 1 isothermal, step 2 isobaric or adiabatic? What is happening in vapor compression cycle? Do you understand the question? Yeah, step by step. So why don't you do images.google?
This is images.
Okay. Okay.
It must be, some other image must be having.
Yeah, just step by step. Yeah, this is right.
I think this one is somewhat.
Yeah. So there is heat out, heat in. Yes, very good. You have pressure here. And what is this? Volume. Right? So this is an expansion process. This is a compression process. This is a condensation process. So what kind? So this is a vapor compression system, right? So can you see something that might be a little bit more easy for you? That's the Carnot cycle.
Something easier would be.
Yeah, very good. So it has to be a cycle, isn't it? Because you're putting in work to get heat out of a colder region and dump heat in the hot region. So clearly you have to put in some work. So here it is mechanical work that you're putting in order to compress and so on, so on. In parallel, what will be the kind of work that you will be putting in as far as magnet is concerned? That's really the question you should ask, right? So why don't you come up with an analogy?
So we found another diagram, but I don't think this is a vapor compression cycle.
That is different. It's not. It's not. It's actually a engine. That's a Brayton cycle. That's different.
Yeah.
So just look for refrigeration. Surprised that you are not getting it. So
We just search for vapor compression cycle. Did you get anything else? This
dot
image,
Google.
Oh, this is the image. So here is the better image, I think. Sir, this one I think is a better image.
Refrigeration cycle. 1 second. There you go. So
This one is a bit.
basic refrigeration cycle. This is very basic. So this might be a little easier.
So here also one cycle is there.
Yeah. Okay.
Cold refrigerated space.
Yeah. So you can use either of those images. That's right. Did you get anything that is helpful for you?
So we're just going through some Carnot Cycle isothermal additivity.
Yes. Why don't you just look at vapor compression cycles?
Yeah.
This is the vapor compression cycle that we understand almost.
Why don't you try looking at an image, because images.google.com, and here let's say refrigeration cycle. Okay, now let's see what comes when you do that. So you have something like this or this. This is the simplest way of representing it, because you can see it in the form of steps, right? You see step 1, step 2, step 3 and so on. So what is step 1 that you find?
So step 1 is work, input work.
Yes. Okay. What are you putting in work for?
We are compressing.
There is a compression step. Very good. There is a compression step. So when you are pressurizing, what will happen to the temperature? It will increase. Very good. What will happen when you expand, when you allow the same gas to expand? What will happen to the temperature? Decreases. So this decrease in temperature, can this be used for refrigeration? Obviously, that's. What's that? No. So if you allow the volume to expand by itself, so volume as no. So if you okay. So why don't you discuss with one another? Yes. Why don't you discuss with one another? So he claims that PV is equals to nRT. So as volume should increase, so should the temperature. That's his claim. Now let us.
At constant T actually.
Yeah. So no. But why don't you discuss this case? So he says, why should the temperature reduce when there is an expansion? Why should the temperature reduce when there is an expansion by the gas? And under what condition will temperature reduce?
Then PV becomes constant. This is Boyle's law.
Yeah.
But when I allow temperature to as a volume is constant.
Very good.
T is proportional to T. This is Charles' law, I guess.
Yeah. So the key here is, see, when you are allowing the volume to expand, okay, whether or not the temperature decreases depends upon whether it's an adiabatic process or isothermal process and so on, right? So if it's an adiabatic process, that means you are not giving any energy, you are not allowing any energy to come out. What would happen when there is a volume expansion? The gas molecules are working against the walls of the container to expand. So, right? So they are losing their internal energy. So what would happen as a consequence? The temperature would decrease. So that's
delta U is Q minus W. So if I
correct.
keep Q is equal to 0 in adiabatic, delta U is minus W.
Correct.
So if it expands, W is negative.
Right. So the easiest way to think about it is I have a system, I am allowing it to work and I don't give it any energy. So clearly it's expending its energy, internal energy. That means clearly there will be cooling. Is it clear? So it has to be an adiabatic expansion for the cooling to happen. So what combination of isothermal and adiabatic processes are required for refrigeration? Once you get that, then we can do the mapping for magnetic systems, right? So what combination of isothermal and adiabatic processes are required to achieve refrigeration? That's the question. You understand?
Isothermal, adiabatic, there will be a cycle.
Okay, so what does that, very good. So what is that cycle looking like? Why don't you draw? So
I use the convention that work done by the system is positive and work done on the system is negative. So now
good, that answer is right. So, but now you'll have to draw it and show it to me, okay, and explain what is actually happening. You can write it in the form of steps also. So you can say I have a hot body, I have a cold body, I want to keep the cold body cold, I want to transfer energy from cold body to hot body because this cold body is sitting in an ambience, okay, and to keep it at a lower temperature I need to constantly extract energy from it. So that is the business of refrigeration, right?
that is the way I understand.
Okay, very good. So you understand? Yes. Okay. So now what are the steps in refrigeration? Steps you need to be operated cyclically for refrigeration to be achieved?
So first of all, isothermal I will go.
Okay.
Where pressure will be constant and volume will be same. Then again I will
Why should isothermal have constant pressure? Isothermal would have constant temperature, I agree. So isothermal will have PV is equals to constant. So P and V will be inversely proportional. For an adiabatic system, PV power of gamma, where gamma is greater than 1, is what is kept constant. Correct? So with this as input, why don't you change your diagram? You understand the question?
So just
Yeah.
let me draw it and then I will see.
You can discuss with one another. You can
right.
also
Right.
write out steps. Okay?
Yes, sir.
So you are thinking correctly only. Now we just have to put some structure to it. So what you are saying is I need to have some combination of isothermal and adiabatic process. 100% right. Now let me structure it. And then once I structure it and get the details, I will do the mapping to magnetism. You understand?
This is the input work. Okay. So this is the diagram. So first we should analyze each step.
You just write out the steps. So step 1, there will be, let us say, compression of some sort or expansion of some sort. So if it is a compression or expansion, is it an adiabatic compression? Is it an isothermal compression? What is happening? Write it out. And you have two temperatures, let's say T1 and T2. T1 is lower than T2. You don't need too many equations. You just have to think in terms of what you already know. So in one case, PV is constant. You have studied this in high school. Isothermal systems are one in which PV is a constant. Adiabatic systems are one in which PV power of some gamma is a constant. So I am saying that, okay, you go from this mode of operation where PV is a constant to a mode of operation where PV power of gamma is a constant. Okay, and you play with it. Let's see what happens. And you have chosen to have a PV diagram, that is all right. But then tell me, where are you cooling, where are you heating? That's also important, right? And whether your coolant is in contact with ambient, whether it is in contact with environment, with the region that you want to cool down, these are all important questions. So let us get the details right.
I think this will be isothermal compression.
Okay.
Because our purpose is to, in a refrigerator, it takes the heat out of the system, right? To
Yes.
cool it down.
Okay.
So heat exchange will be occurring.
Yes. So from the cool system, I need to actually extract out
Yeah.
energy. So at that point, I have to be in touch with the cool system. Correct? But in order to extract out energy from this cool system, I want energy flow from this cool system into the refrigerant. So what should the refrigerant condition be? How can I actually achieve this energy input?
Refrigerant should be cooler than the cool system because heat flows from higher temperature to lower temperature.
Okay.
Means for spontaneous
Yes.
flow of heat.
Yes.
So refrigerant should be even cooler than the system.
Okay.
Only then heat will spontaneously flow out.
Okay. So this system, this cold system is actually having this constant tendency to get some energy from the environment. So it gets some, let us say, delta Q. That delta Q should actually be conducted away by this. So this coolant that I am dealing with is some kind of a heat sink. It's not really heat sink in the way you have seen it in a textbook, but it is a coolant. It actually draws that heat. Okay. So it doesn't allow this system that is supposed to be kept cool to warm up. Even when there is a heat flow, immediately it is taken away. Whenever there is a heat flow, it is taken away. So that is the only thing you have to think about. And then I have to go and dump that heat and come back. Correct? So this is a system that is supposed to be cold. As and when there is input of heat from the environment into that particular system, I have to conduct it away. And then I should go somewhere else and dump it. So heat should be rejected. Now for heat rejection, can you have an adiabatic process? For heat rejection, can you have an adiabatic process? By definition, an adiabatic process is a process wherein there is neither heat given away into the environment or heat taken from the environment. So this kind of rejection of heat cannot be an adiabatic process. But it can be an isothermal process. There is nothing preventing that, isn't it?
Yeah.
There is nothing preventing that. So now at least I have found out where the isothermal should be and where the adiabatic should be. At least that I have figured out. So now you write down the steps. You understood? You understood? Yeah? You attempt. It is all right. So as I told you, this is exactly how the business of science and technology works. You know, you try, you might fail, you might have to redesign. It doesn't matter. What do you lose? Nothing.
So this is the heat is coming from that refrigeration.
That heat should look at this first because here so let us look at this first. Heat extracted from source into.
So that cycle is fast, that coolant will expand, so some cooling will happen and it will release to whatever.
Right. So you just have to use the definition of two words. Adiabatic, that's all. Nothing else. You don't need any other definition. With that you can come up with the concept of refrigeration. I just told you how. So now you write it out. As I told, just dare to dream, dare to design. 1, 2, 3. It's okay if it is wrong. You are drawing diagrams quite right. So the big difference, of course, is if PV is a constant, this and this slope, of course, would be different, right? So this cannot be perfectly flat. This is what is called as an isobaric process, where the pressure is constant. If the volume is constant, it's called an isochoric process. If temperature is constant, it's called an isothermal process. If there is no heat exchange, it's called as an adiabatic process. These are things you have studied in your high school. So I'm just asking you to use that, nothing else. So adiabatic processes are where the temperature of the system of the coolant should in principle either be increasing or decreasing. Correct? In isothermal stages, you can exchange heat, right? Adiabatic processes are wherein you are likely to either increase or decrease the temperature of the refrigerant. So these are the two facts that you have arrived at by the definition of isothermal and adiabatic process. So let us look at this. And you will appreciate, I hope, the importance of a material as it stands right now. So as of now, you have appreciated the vapor. and typically materials engineers look at solid phase. So the question is really, can you replace this refrigerant, which is a vapor phase refrigerant, with something that is a solid? And my response was, why don't you work with a magnetic system, to which you are doing work when you are applying a magnetic field. Alright, you are doing work when you are applying magnetic field, so it is equivalent to doing work on a vapor. So magnetizing a magnet is like compressing a gas. So for example, so this is actually taken from Wiki, so it's open source, it's from, sir, are you able to see? So the most crucial steps are the extraction of heat. Okay, so here as far as the system is concerned, it is losing heat, and the extraction of heat here. So how many of you understand this? So the system, it's warming up, hence it loses temperature to the, hence it loses heat to the environment. It comes to temperature T, it cools down, comes in contact with the room, it takes up the heat from the room and goes to a higher temperature. You understand? Now you apply pressure, so it becomes hot. It loses that heat that which it had gotten here. Okay, it loses the heat and then it becomes cold. When it is cold, you allow it to expand. It becomes colder. It's in contact with this room, and hence it extracts heat, and so on and so on. So which one is the isothermal process and which one is the adiabatic process as far as this is concerned? So wherever there is heat exchange, clearly what kind of process is it? So this T plus delta, so here in this particular case, so I have this process here. This one is a process wherein it's undergoing expansion. What kind of expansion is this? What kind of expansion is this? There's no heat exchange. So what kind of expansion is this? Adiabatic expansion. So I have an adiabatic expansion. Here, there is a compression. There is no heat exchange. So what kind of compression is this? Adiabatic compression. Now here there is loss of heat. And what is also happening is that there is a change in temperature. So can you actually call this an isothermal process? So what kind of process is it? So what is actually changing here? It is an isochoric process, isn't it? So this one is an isochoric process. So here it's an isochoric process, the way it is actually shown. So the volume is kept constant. The volume is kept constant here, all right? And so on. So now do you understand? So can you think about a different refrigeration cycle, as you pointed out, wherein you have a combination of adiabatic and isothermal? Is it possible? Is it impossible? You had suggested that. Is it allowed? Is it disallowed? This is a homework question. All right. But now, in keeping with this, okay, now let me draw a magnetic analogy. When it heats up, I am doing work on the system. So I have a magnetic system. It is full of magnets that are disordered, that are oriented in all possible directions. I apply a magnetic field, it gets oriented. Okay. So it is like compressing this gas, doing energy, investing energy in it, and as a consequence, it heats up. Then I remove energy from this. It cools down, okay, to the ambient temperature, and then I am basically removing the magnetic field. So this is demagnetization. So it cools down. So it is the equivalent of expansion, all right, and then I am adding energy to it. It basically comes back to a temperature T. Where is this energy coming from? From the room. So it's extracting energy from the room. So I can actually develop a magnetic refrigerator as a consequence. So whether or not I develop a magnetic refrigerator or not will depend upon whether the system will respond to the magnetic field. So higher the magnetization, better it is. Higher the entropy change associated between this state, between this state and this state, better it is. You understand? You understand? So it's in perfect analogy with the vapor phase, vapor compression refrigeration system. You understand? So I can in principle as a consequence use a magnetic material. And what are the magnetic properties that we explored in the last class that it might be relevant here? The magnetic properties that we explored in the last class that is relevant is magnetic susceptibility. Do you think the system should have high susceptibility? Absolutely. It has to respond. Okay, so if it is a relatively ferromagnetic system, that is better. If it is a magnet, a proper magnet, it's better. But at the same time, that alone is not sufficient. It should also have a substantially high entropy gain associated with disorder, with demagnetization. You understand? So that is the take home. So can you use materials in a very novel and innovative manner? The answer is yes. So can I replace the AC system here with a magnetic AC? The answer is yes. You just need the right material. I mean, it might cost a great deal, and it actually does, because one of the champion materials is something called gadolinium. It costs a great deal. It's a rare earth element. Okay, but in principle, is it possible? The answer is yes. So you can cool this room by using a magnetic system. So magnetic refrigeration is actually possible. Isn't it an interesting idea? Very interesting idea, isn't it? So this is the reason why material properties need to be explored. This is the reason why it is enjoyable to explore material properties. It opens up the world of design for you. It opens up engineering possibilities for you. Now, in keeping with this as the diagram, okay, this as the cycle, can you now just redo your diagram? Just redo your diagram now. So you have this as the cycle, so just redo your diagram, refrigeration cycle.
What do you mean redo?
So some of you have actually done something, you know. You have done something that needs some correction. So why don't you spend some time? So let me take a look at your PV diagram, for example. Do you want me to show, what would be the PV diagram that will help explain this, or the PT diagram if you want to draw? Okay, why don't you spend some time
For magnetic refrigeration.
For magnetic refrigeration or vapor phase refrigeration. For vapor phase refrigeration, it is PT diagram or PV diagram. For magnetic refrigeration, it would not be that, isn't it? Because analogous to volume is some entropy term. Okay, and analogous to pressure would be the applied magnetic field H.
Yeah.
Correct? So you will have to think slightly differently for that. So for the time being, you can spend a few minutes at home thinking about what the PT or the PV diagram for this refrigeration cycle would look like, and hence what the corresponding magnetization cycle would look like. Okay.
Magnetic field versus entropy diagram.
So magnetic field here is analogous to pressure.
Yeah.
So if you have, right, magnetic field here is analogous to pressure.
Yeah.
Correct? Do you agree? Now then if you consider temperature, temperature is temperature. There is no difference. Correct? Now what else? Volume volume in this particular case is related to magnetization, because if you think about it, here the volume reduces, and the magnetization is, so in this particular case, let me see. So you have applied here you have magnetization going to 0, you have a expansion. So the entropy, that means the disorder of magnetization, that means the disorder associated with these magnets corresponds to an increase in volume, right? That means lower the magnetization. Yes. So you will have to, as a consequence, think in terms of applied magnetic field, magnetization, temperature, and come up with a parallel between vapor-based refrigeration and magnetic refrigeration. You understand? So that's your homework. So spend some time doing that and also discuss it with one another. You can WhatsApp your best images that you have come up with on the WhatsApp group that you have created, and so on, so on. Okay? So, but do you understand, do you appreciate it now? The fact that instead of using vapor, you can actually work with magnetic materials. Do you appreciate that? So that was about magnetic properties and how magnetic properties could be put to very, very good use. All right. Now the next thing that I want to discuss has to do with optical properties. The following are optical properties. Why don't you read these optical properties? Okay. So reflectivity, transmittivity, absorptivity. So there is some definition that I have given there. Refractive index, and we'll look at some numbers associated with this. Okay, so let us look at refractive index associated with some of the materials that are around us. Refractive index is the ratio of the speed of light in vacuum divided by the speed of light in that material. All right. So what are some materials that you can think of around you? Glass. So why don't you look up the refractive index of glass? It will vary, but let us take a look at what the refractive index looks like.
Around 1.5.
1.5. So what will be the velocity of light in glass?
1.5 times
Lower. So what is that?
So 3.
2 into 10 to the power of 8 meters per second, because it is 3 divided by the refractive index, and 3 divided by 1.5 is 2. 2 into 10 to the power of 8. So let us take another material around us, let's say water. What is the refractive index of water?
1.33.
1.33. So what will be the velocity of light in water?
3 by 1.33.
You are welcome to use your calculators. 3 divided by 1.33. So can you show me your workings? You can show him your workings if necessary. Correct. So it will be 2.25 into 10 to the power of 8 meters per second. So refractive index is valuable, and I have added a little bit of detail here. Refractive index, the way you have studied in high school, it's a real number, and the way in which those databases are represented, it's a real number, but in truth it's actually a complex quantity, and I want you to think about it. You have in your high school and so on thought of current as a complex quantity, some constant times e power of j omega t and so on and so on, and it turns out that refractive index is also a complex quantity, and I want you to think about it. Just spend some time thinking about it, okay? So I have made a note, and this will be given as part of your handout, but you'll have to think about it. Why should it be complex? What does it mean to say that refractive index is complex? It's a very strange thing, no? Because the way it is defined, it is speed of light in vacuum divided by speed of light in that particular material. How can it be complex? But it is complex, okay? So think about it. The other one is reflectivity, transmittivity and absorptivity. So these are the definition. So if I have a material, I shine light into the material, all right? And if I know the reflected light intensity and the overall light intensity, I can find the ratio and find reflectivity. I can do an analogous exercise to get transmittivity and absorptivity, okay? So here is a question. If I increase the absorptivity, what will happen to transmittivity? Discuss with one another. If I increase the absorptivity, what will happen to the transmittivity? Discuss. Discuss with one another. And do you expect some relationship between the amount of light that is reflected, absorbed and transmitted? What happens? Do you understand the question? So what happens to the transmittivity when absorptivity increases?
Decreases. If the reflectivity remains constant, then the transmittivity should decrease.
Decrease. Very good. That's correct. That's the right statement. So if you can keep one of the parameters constant, then as absorptivity increases, the transmittivity would decrease. And the way absorptivity, reflectivity and transmittivity is defined, let me call transmittivity T, absorptivity A, reflectivity R. What is the relationship between all three of them? Why don't you write it down?
R plus A plus T equal to 1. Yeah.
That's all. R plus A plus T is equals to 1. Correct. That's rat is equals to 1. R plus A plus T. Okay. So I have given some data here from the IOFA database. It's a Russian database on semiconductors. It's a very useful and powerful database. So I have pulled out data, optical data for aluminum nitride and silicon carbide and a few other materials, just for you to have a feel. For example, dielectric constant here is about 8. Dielectric constant at very high frequencies comes down, and this inevitably be the case. most materials will have a low dielectric constant at high frequencies. That means if I am shining light of very high frequencies, the dielectric constant would, if I am applying AC of very high frequencies, the dielectric response would actually be weaker and weaker and weaker. So this is generally the case, and is also the case with refractive index. At very high frequencies, the refractive index lowers. So this is by and large very common. I think from there it's difficult for you to see the data, isn't it? Are you able to see the data from there? No. So but I'll read out the data. So for example, dielectric constant at high frequency for silicon carbide is 6.52, all right, and the refractive index in the infrared is 2.55, but otherwise the refractive index is a little above 3, all right, and likewise for aluminum nitride, the dielectric constant is 9.14 for static DC application. For high frequency, it becomes as small as 4.84, so it actually reduces as a function of frequency. For infrared range, the refractive index is somewhere between 1.8 to 2.1, but it goes up substantially when it comes down substantially when you go to visible and UV and so on. So there are some numbers that have been given here. And I got all this data from the IOFA database. So you are welcome to look at it. It's a free database on semiconductors. I just pulled out this data for semiconductors. Okay. Please do spend some time looking at just IOFA, IOFFE, IOFA database. Look at various semiconductors and the numbers associated with them, and look at things like the band gaps and so parameters that we have actually discussed in this class, and also parameters like this, reflectivity as a function of lambda, absorptivity as a function of lambda, transmittivity as a function of lambda, and so on. So you will get a sense of the data that is actually available out there, and by and large this kind of data is useful for designing optical materials, for choosing optical materials for specific applications. Okay, and in perfect analogy you can define acoustic parameters. For example, reflectivity, transmittivity, absorptivity associated with sound waves in perfect analogy, okay? Because if I know the incident intensity of sound wave, I know the transmitted intensity of sound wave, okay? I know if I know the absorbed intensity and the reflected intensity, I would be able to define transmittivity, absorptivity and reflectivity associated with sound waves. So these coefficients, by the way, exist even for optical properties. So transmission coefficient, absorption coefficient, reflection coefficients and so on exist. So there is perfect analogy in that sense, and not complete analogy, but there is, as far as these coefficients are defined, an analogy that exists between acoustic properties and optical properties. Not surprising because both of them are waves, but they are different in many ways. You know, light is an electromagnetic wave, acoustic waves are longitudinal waves, right? So they are really matter waves. So here is a question, the velocity of sound in a crystal. So how many of you remember what crystal is? So crystal is a perfectly periodic arrangement of atoms. So now discuss with one another, given this thing that we stated, it's a matter wave, okay? Given that quality of sound waves, does the velocity of sound depend upon direction in a crystal? That's the question. So please discuss with one another. Do you understand the question? So I have a crystal, I'm going to send sound this way, this way, this way. Are the velocities going to be similar? Are they going to be different? That's the question. Okay. So please discuss with one another.
It will be similar. That's whatever sound it will.
So the sound wave, as far as you are concerned, you think that the wave velocity will be the same, sound wave. Why do you think so?
Because the atoms are arranged in a similar way, so that whatever sound will carry by the atom, it will be in similar way.
So let us think about a cube. Okay, so I have a box like this. So this is the system. So here the atoms are sitting close to one another. They are sitting here. They are sitting here. So here the atoms are sparsely present. You know, the planar density seems to be lower. Here the planar density is higher. So if I'm going to send the sound wave in this direction as opposed to in this direction, do you expect a difference? Obviously, there will be a difference. Yeah. Okay, what's your response?
So it should depend on the direction.
Correct, absolutely. It should be depend on the direction. So the explanation I gave there was, suppose you have atoms sitting here like this, you know, and I'm going to send a sound wave in this direction as opposed to sending it in this direction. Clearly the atomic density here is different when compared to the atomic density here. So the jiggling of atoms would be different, and hence the propagation of sound would be different. It would be having very different velocities in this direction and very different velocities in this direction. Okay. So makes sense, right? Makes sense. And it would be very different if I sent it like this, between this point to this point. So it would be very, very different. So the velocity of sound as a consequence is not a single parameter, though you have studied that to be the case in your high school. It is not a single parameter. You have to define the direction of the crystal as well. Okay. So with that, we come to the end of this session. So can we summarize a few learnings from this session? Few learnings. Can you discuss with one another and come up with some points that I'll write down in the board? Okay. So a few things that you have studied, that you learned, okay, that might be relevant as far as your own learning experience is concerned. So jot it down. Can you jot down some things that you have studied today? Okay, so what are a few things that you learned?
First we learned about the different steps involved in refrigeration.
Okay, so you learnt about refrigeration and the fact that there could be an analogy between vapor phase refrigeration and magnetic refrigeration, right? So this is very widely used. This is not widely used, but if you could invent a magnet that could provide the necessary entropy changes, the necessary amount of magnetization, in principle we could have a magnetic air conditioning system instead of having an air conditioning system like the one that we use here. Okay, so that's what we found. Here you use a combination of processes, isochoric and adiabatic processes. Okay, in perfect analogy you can actually think about magnetization, demagnetization processes. Okay, pressure is analogous to magnetic field and volume is analogous to magnetization. So these are thermodynamic parameters and so are these. So these are thermodynamic parameters, correct? That go into determining the work that is done on the vapor, and these are thermodynamic parameters that determine the work that, these are also thermodynamic parameters that determine the work that is done to the magnet. Okay. What is another thing that you have studied? Huh? Refractive index, reflectivity, absorptivity, transmittivity associated with both sound as well as light waves, right? Very good.
We learned that refractive index is actually a complex one.
Yes, both dielectric constant and refractive index are complex quantities. That is right. Anything else?
We learned that dielectric constant becomes lower at higher frequency.
That's right. So at higher frequency, the dielectric constant becomes lower and so does the refractive index. In fact, there is a very interesting relationship between dielectric constant and refractive index. Refractive index is written as square root of the dielectric constant. So this is a very simple relationship, and this is also the reason why the dielectric constant, when that reduces, the refractive index also reduces. Okay. Anything else?
The velocity of sound through a crystalline solid depends on the direction.
Yes. So the direction of light and the direction of sound, in fact both of them would be direction dependent. The velocities would be direction dependent. So there is anisotropy associated with crystals. It's expected. It's not surprising. It is expected because of the example that we saw, right? Anything else that you studied?
In general, we can manipulate the properties of material for practical application.
That's right. So if I knew, for example, to achieve a certain kind of performance, to match a certain kind of performance here, I need to have a certain combination of magnetization, susceptibility, entropy change associated with magnetization, demagnetization. I could explore that. In fact, that would be research. That would be a project, correct? Yes. Anything else? And I also told you that the magnet that actually seems reasonable for this application is gadolinium, and it's a rare earth. It's extremely expensive. So finding suitable replacements for it would be certainly an interesting direction as well if you wanted to realize magnetic refrigeration. All right. Anything else?
Two ways are there. Either you can work on a material based on its properties to achieve the goal, or to design a material to get certain properties.
That's right. So you can work with existing materials and say this will be the performance of my magnetic refrigerator. And you could find some niche applications for that particular magnetic refrigerator. Absolutely. Alternatively, we could get ambitious and say, I will need to develop a magnetic material in order to compare, to give comparable performance to the kind that I am seeing here and so on. Okay. Very good. That's right. So those can be two approaches. So I could say, okay, for this particular performance of the magnetic refrigerator, this is the application that I can envision. Right. Very good. Anything else? Okay. So the teacher is looking at this. Please note, I populated it with a set of words that are all interconnected to one another. So this enables a visual representation of what has been taught, what has been learnt. And when you get your students to do things of this sort, they are thinking about connections between various ideas and concepts and facts and figures and information and so on. And as a consequence, exercise like this can be very helpful. Now this exercise is called a mapping exercise. There are different kinds of mapping exercises. For example, you could start with an idea and you could actually develop a radial pattern. Okay, or you could have a knowledge tree. You could say I have a bunch of boxes and these boxes are connected to some other boxes. Okay, and these are all facts and figures or set of ideas, concepts, keywords, and these could be connected to one another. So you could use interconnects and so on. So this kind of a tree diagram is widely used, and this could be used to develop something called the concept map. And something like this is called a spider diagram, or it's also called a mind map. So it radiates out. So spider diagram tends to be a simpler form. So it basically looks like a spider, but mind map can actually be just a radiating pattern, visual representation of information, very helpful for students. In fact, there's a lot of literature that suggests that when students represent information in this form, they understand interconnectivities better. They also think more creatively and so on. So it can be highly encouraged as part of classroom exercises, and something like this can also be encouraged in classroom settings. So with that, we are done with this session of this Swayam course. Thank you.